Hello everyone, in this video we are going to talk about the reactions at the alpha carbon of carbonyl compounds. So let's get started. So in the last chapter we talked about the reactions of the carbonyl compounds. So one of the basic reactions of the carbonyl compounds is the reaction with the nucleophile. So to analyze this, to realize this, we know that the structure of the carbonyl compound has a electropositive carbon, which is right here, and an electronegative oxygen. So when a nucleophile will come and attack the when a nucleophile comes and attacks the carbon, it's going to thrust these electrons onto oxygen, giving rise to the tetrahedral intermediate. This is what we have seen in the previous chapter. But carbonyl compounds also have also got another site for reactivity, and this site is actually called as the alpha carbon. Now alpha carbon is the carbon that is adjacent to the carbonyl group. So here is the carbonyl group and this is the alpha carbon, and any hydrogens that is attached to the alpha carbon are called as alpha hydrogens. And a special thing to say about this alpha hydrogen is they are acidic. So meaning that if there is a base present in the solution, then it's going to go abstract this hydrogen and these electrons will go up to the carbon, forming a carbanion. This carbanion, which has an adjacent carbonyl group, has got a special name which is called as enolate. Okay, now let's talk more about the acidity of an alpha hydrogen. So we know that the carbon and the hydrogen has similar electronegativities. When the hydrogen is attached to a carbon, which only has this sp3 carbon, then it is going to be not acidic at all, meaning that you cannot pull that hydrogen away from the carbon. But if the hydrogen is attached to an sp3 carbon, which is adjacent to the carbonyl group, then the hydrogen can be lost readily in the presence of a base. So if you take the structure of an aldehyde, ketone, and an ester, you can see that the pK of these compounds are roughly between 16 and 25 depending upon the nature of the compound. So let's say what happens when you remove one hydrogen from these compounds. So if you remove the hydrogen from these compounds, it is going to form the carbanion, but that carbanion is stabilized between two different resonance structures. So you can see that these electrons can go up here and the double bond breaks and it goes to the oxygen. So you can see that there are two different resonance structures for this base, and because the base is stabilized because due to the resonance contributors, the acid that it came from should be a stronger acid. Okay, now going to the slide, we can answer why aldehydes and ketones are more acidic than esters. So if you look into the pK values of aldehydes and ketones with that of the esters, you can see that the esters are relatively basic. So the reason for that comes from the stability or the electron donating ability of the oxygen, another oxygen that is present in the ester group. So these electrons right here are not completely delocalized onto the oxygen. There is some kind of competition that exists between the oxygen, but the lone pair on the oxygen and also the lone pair on the carbons, the delocalized electrons on the carbon. So the electrons on the alpha carbon are not as readily delocalized onto the carbonyl oxygen, and the oxygen of the OR group of the ester also has a lone pair that can be delocalized onto the carbonyl group. So the two pairs of electrons compete for delocalization onto the same oxygen. Okay, there are also other compounds where the alpha hydrogen is acidic. So say for example you take nitroethane, and again this is the alpha carbon, because if you consider this is the functional group and the alpha carbon is the carbon adjacent to the functional group, and after this when you have a base, this goes and abstracts this hydrogen and it's going to form the carbanion, and that carbanion is actually stabilized by different resonance structures. And again, here is the functional group and this is your alpha carbon. Once the hydrogen has been abstracted, it's going to form the carbanion. The carbanion is actually stabilized between different resonance structures. And the same thing goes here as well. So once the hydrogen has been abstracted, it is going to form the carbanion, and that carbanion is going to form enolate-like structure. Okay, now what if the alpha carbon is in between two carbonyl groups? Okay, let's analyze some of these structures here. So here is a compound. So this is called as beta diketone because you have two ketones, functional groups, and the second keto group is actually in the beta position with respect to the first keto group. So you can see if this is your first ketone group and this is your alpha position and this is your beta position, you can see that this is a beta diketone because it has two ketones and the second ketone is in the beta position. Okay, so when you have two carbonyl compounds and when you have a methylene group that is flanked by the two carbonyl groups, then you can tell that this hydrogen is very, very acidic. So you can compare the pK of it. So the pK is actually equivalent to 8.9, which means it's very, very acidic compared to the aldehydes or the ketones, which had the pK of roughly between 16 and 20. Okay, and the reason for this is for this high acidity of the alpha hydrogen is again going to come from the resonance structures. Suppose if I'm going to remove the hydrogen from here, let's imagine that there is a base. The base is going to go grab this hydrogen and those electrons will be thrusted onto this carbon and that's going to form a carbanion. So here is your carbanion. Now this carbanion, these electrons on the carbon can be delocalized in two different ways. So here is the first way that it can delocalize. These electrons can come up here and the electrons from the double bond can break and it can go on to the oxygen. So here is one structure and the electrons on the carbon can actually go on to this side and it can thrust these electrons onto the oxygen and it is going to give you another structure. So basically there are three different resonance structures for this compound, and because of which the base should be readily stabilized and therefore the acid that it came from should be very acidic. Okay, so now let's see whether we are able to attempt the structures of these compounds. So beta keto nitrile. How do we write the structure for beta keto nitrile? So we know that this is a nitrile group and this is your alpha carbon, and on the beta position you're going to have a keto group. So that's the keto group right here. And beta diester. So here's again, these are just a general example. You can have different groups, different R groups. Let's imagine that this is your R group, this is your R group. Here in this case it is a methyl group, but you can also have an ethyl group or a propyl group depending upon the compound that you wanted to write down. Okay, so this is a diester. So here is your first ester group and second ester group. If you consider this as your first ester group, this is your alpha carbon, this is a beta carbon, and that's a beta diester. And beta keto aldehyde, this is your aldehyde, that's the basic functional group, and this is your alpha carbon, this is a beta carbon. So this is beta keto aldehyde. In the next video, we'll be talking about the keto enol